I think the title slide maybe sets a record for the density of acronyms and initialisms. OSS is not the Office of Strategic Services, but I'll be clearing this up in a minute. The presentation is about phase conformance and the Ada programming language, and that leads to a fairly natural structure. First, I'll give a brief intro to the phase approach, then an equally brief intro into phase conformance, and then explain why phase conformance is a challenge for the Ada programming language. That leads up to the grand climax when I explain how these challenges have been met. So let's start. In a nutshell, the phased approach is about source code portability. Recompiling a software component and then deploying it in an airborne system on a new platform is a lot cheaper than redeveloping it. Okay, I'll need one more nutshell. The phased approach also recognizes that components might be at different levels of safety or security criticality, and that has implications on partitioning as well as API and language feature usage. The solution is documented in detail in the phase technical standard and has several aspects. First, a reference architecture that reflects good software engineering practice with a separation of concerns and encapsulation of platform dependencies. The architecture consists of a set of so-called segments, and these correspond to areas of functionality. The PCS contains application components, which carry out the system's mission. The TSS provides communication services that are used by the PCS software, and the OSS supplies the operating system and related runtime services through a platform-independent API. There are a couple more segments, and you can refer to those in the phase technical standard for details. Second, and the way that the phase technical standard approach brings portability while addressing safety and security, the standard is big on open and standard interfaces. It defines subsets of the POSIX and ARINC 653 APIs corresponding to the level of assurance that is required. There are 4 subsets known as profiles. In increasing levels of generality, these are the security, safety base, safety extended, and general purpose profiles. There are analogous subsets of features from several standard programming languages: C, C++, Ada 95, Ada 2012, and Java. 3 subsets known as capability sets are defined for each language: safety base and security, safety extended, and general purpose. Through open and standard interfaces and language features, the phase approach avoids vendor lock-in. Finally, an important part of the phase approach is a rich data modeling technology. This way, the data that's communicated between components is interpreted consistently, so we don't end up in a situation where one component thinks that distance is measured in kilometers, while another one treats the value as miles. Now, as a developer of airborne software, you might want to produce a component that meets the requirements of a specific segment targeted to a specific profile and capability set. Great, you're developing, in phase jargon, a unit of conformance, or a UoC. All well and good. Now, how do you show that the UoC actually meets the requirements? That's the subject for the next slide. The phase technical standard defines lots of requirements that UoCs need to satisfy, so it's important to have a well-defined process for checking whether a UoC in fact meets the requirements for its targeted segment, profile, and capability set. Now, here I have to point out that not all segments are treated the same, and in fact, the OSS is special since its implementation is intrinsically platform dependent. So in this presentation, when I talk about conformance, I'll be referring to conformance for UoCs that are not targeting the OSS. To be honest, in practice for Ada, it will almost always be the PCS, but the principles apply also to the TSS and other segments. There are a number of things that need to be demonstrated for phase conformance. For example, a conformant data model, but for Ada, there are 2 that stand out. The UoC developer, or software supplier in phase terminology, needs to show that the UoC does not use any POSIX or ARINC 653 APIs that are prohibited from the targeted profile. And likewise, that it does not use any language feature that its targeted capability set prohibits. As an example, if an Ada UoC is targeted to one of the safety capability sets, then it cannot use the full Ada tasking model. It needs to stay within the so-called Ravenscar subset. So the Conformance Test Suite, or CTS, needs to check this. In theory, this isn't a big deal. Other software certification standards have similar requirements, and the developer submits the source code to the certification organization, together with evidence from either a qualified static analysis tool or else a source code review. But for phase conformance, there's a kicker. Conformance verification cannot require that the UoC supplier expose the UoC source code. That's for legal reasons. The code might be classified or proprietary. The solution is for the CTS to use link time tests. Pay attention because here's the critical point. The UoC supplier needs to compile the UoC with a tool chain that includes several specific runtime libraries. In fact, these are stub libraries, just header files, since the code will not be executed. First, a so-called gold standard library that contains, among other things, the API for the permitted POSIX or ARINC 653 profile. Second, a compiler-specific runtime library that contains the API for runtime functions that are invoked from the compiled code. An example is the GCC lib, which includes functions for things like stack unwinding and perhaps a 64-bit integer division. The UoC supplier submits the resulting UoC object code to the CTS. The CTS attempts to link the object code with the gold standard library and the compiler-specific runtime. If the link fails, there's an unresolved reference. This means that the UoC is invoking a function that is not permitted in the targeted profile or capability set, and the conformance verification thus fails. But the inverse is not necessarily true. A UoC may pass the link time test, yet still fail to conform. This can happen for several reasons. First, there are capability set restrictions that are syntactic in nature and unrelated to runtime functionality, like restrictions on generics or templates. Violations won't be detected by a link time test. Second, the link test cannot detect if there's a source code invocation of a function from the compiler-specific runtime library. These calls will exist from the object code, so the link will work, but they're not allowed in the source code. So to handle these cases, the UoC developer will need to prepare evidence from source code inspection that such violations do not occur. Finally, it's important to realize that the CTS is only checking if the proper interfaces and language features are used. It does not verify fitness for purpose or show that the UoC meets any particular safety or security standard. The process that I just described, link time tests coupled with some amount of inspection evidence, works pretty well for C and C++, but less so for Ada. On the next slide, we'll see why not. It doesn't work so well for Java either, but that's a subject for some other presentation. The main difference between Ada and C or C++ is that Ada source code reflects runtime functionality like concurrency, not by a call on a function from a standard API, but instead by language standard syntax. Here's an example. The C code on the right creates a thread by an explicit call on a POSIX function, and this function is permitted in all the profiles. In Ada, you create a thread, or task as it's known in Ada, not by an API call, but rather with a standard syntactic feature known as a task declaration. The Ada source code is compiled into object code that calls functions in the compiler-specific runtime, and the API for this library is different for different tool chains. Ada Core's Gnat library does not have the same interface as the Greenhills library. Additionally, the compiler-specific runtime needs to support at least what is permitted by the targeted capability set, but it's allowed to supply more, possibly including runtime features that should be prohibited. That's because compiler vendors cannot be expected to come up with runtime libraries that exactly match the face features. So that raises some questions. Two are specific to Ada, and one applies to all the languages. First, how does the UoC supplier or the face verification authority know whether a given restriction is enforced by the toolchain and compiler-specific runtime, or instead requires source code inspection? Second, how is the compiler-specific runtime supposed to be installed as part of running the CTS? And third, which is not specific to Ada, how do we verify that the UoC source code is not calling a function from the compiler-specific runtime? These questions need to be addressed if the CTS is to support Ada. Oh, by the way, there's no funding for updating the CTS, so any solution needs to work with the existing package, which does not generate either a gold standard library or a compiler-specific runtime for Ada. So let's see how we've solved this. The first issue is how to determine whether a capability set violation is detected by a given Ada toolchain and its compiler-specific runtime for the targeted capability set. To do this, we've come up with a test suite known as the Toolchain Capability Assessment Test Suite, or TCATS. The tests were directly derived from the Conformance Verification Matrix, or CVM. This is a copy of the requirements from the FACE technical standard, in other words, a list of language feature restrictions for each capability set. These tests cover both Ada 95 and Ada 2012, and all three capability sets: general purpose, safety extended, and safety based and security. Each test case is a short Ada program that uses a prohibited feature. Many of the restrictions result in multiple test cases. For example, one of the restrictions in all the capability sets is that there is no use of Ada I/O. There are multiple top-level Ada I/O packages, so there's a test for each one. The idea behind the TCATs is that when a test is compiled and linked against the Ada toolchain with its stub compiler-specific runtime, the attempted compile and link will either succeed or fail. If it fails, that's good news. That means that what we're hoping for. The violation of that requirement will be detected by the CTS, assuming that the CTS can install the compiler-specific runtime. More on that later. But if the compiler and link succeed, then source code inspection of the UOC will be needed in order to show that the restricted feature is not used. Currently, there are around 120 individual tests in the TCAT suite. These were derived from the Phase Tech Standard 3.2, as augmented with some updates that will go into 3.3. In addition to the TCATs tests themselves, the TCATs package includes a script that invokes an Ada toolchain to compile and link each of the test programs. The script is actually an Ada program that works with the Ada Core GNAT toolchain, but it's tailorable to work with any vendor's Ada compiler. The script outputs a text file indicating for each test whether or not the toolchain detected the violation. The TCATs package also includes a spreadsheet that will be filled in with the results of running the script. The TCATs tests themselves are written in standard Ada and are toolchain independent, but the results may vary from one toolchain to another. The violation that is detected by testing for Ada Core's GNAT Ada compiler might require source code inspection for Greenhills or vice versa. The script can be run and the spreadsheet completed by the toolchain provider, by the UoC software supplier, and by the space verification authority agent. Here's an excerpt from the TCATs worksheet, which hopefully will make some of this a bit more specific. One of the requirements in the Phase technical standard is a ban on Ada's asynchronous transfer of control. This is used for timeouts and event-based programming. It's prohibited for both Ada 95 and Ada 2012 for all the capability sets, and it's documented in several rows of the CVM. In the spreadsheet, we've numbered the requirement. It's R2. Since there are two Ada constructs for this feature, we need two test cases. The test ID indicates the requirement, which test of the requirement, and which capability sets are covered. So the ID for the first test shows that it's the first test for R2, and that it covers all three capability sets: safety base, safety extended, and general purpose. There's no suffix on the test name, so that means it applies to both Ada 95 and Ada 2012. The X's in the columns show that the test applies to both Ada versions and all capability sets, and the standard pragma column shows a pragma that can be used to detect the feature at compile time. The verification method column is blank since this worksheet is just a template, and it will need to be filled out for the toolchain that will be used in the CTS. Another requirement is shown here. There's a restriction against using an Ada 2012 feature, synchronized task or protected interfaces, in a UOC for either of the safety capability sets, but it's allowed for general purpose. Requirement R4 is the ID for this restriction, and the first test is a program that uses a synchronized interface. So the test name shows that it's the first test of the requirement, that it applies to safety extended and safety base, and the A12 suffix means that it applies only to Ada 2012. Asynchronous transfer of control is a runtime feature, so a toolchain will implement it through some functions in the compiler-specific runtime library. If those functions are absent from the sub-library that it's used in those TCATs tests, which is likely, then the usage will be detected by the toolchain. On the other hand, synchronized interfaces are a syntactic feature and do not require runtime support, so source code inspection evidence will be needed to show their absence from the UOC. Okay, so now we know how to check whether a toolchain and its compiler-specific runtime library detect the various restrictions, but how does that runtime get installed by the CTS? That's the job of a toolchain support package that the toolchain vendor will need to prepare. This package basically consists of the documentation and any other files that are needed to do the installation. So there's an Ada supplement to the CTS user's guide with information that either augments or supersedes what's in the user's guide. Ada Core's GNAT support package explains how to install the runtime library for the GNAT 2017 Ada toolchain, which has appropriate open source licensing and supports both Ada 95 and Ada 2012. It also shows how to run a script that derives the stub compiler-specific runtime corresponding to the selected capability set. These artifacts are tailorable to other toolchains, so other Ada compiler vendors can provide analogous information. The third challenge for Ada conformance verification is to show that there are no source code references to functions in the compiler-specific runtime. There will naturally be calls on these functions from the object code, so the CTS link time test is not sufficient. Non-conformant source code that includes an explicit call on one of these functions will link successfully. The solution involves restrictions on compilation unit dependencies, and these show up in the with clauses and parent-child syntax that can be demonstrated by source code inspection. So the UoC developer needs to provide the inspection evidence. By the way, the issue is not unique to Ada. Other languages will need similar rules. To make things more concrete, here's an example of the workflow for running the TCATS test on a specific Ada toolchain with the stub compiler-specific runtime library that's been generated for the targeted capability set. The TCATS package includes a script, actually an Ada program, named build and report status. This program takes a file that lists the file names for the TCATS tests. That's the file tcatslist.txt. For each test that applies to the targeted capability set, the script invokes the Ada toolchain on that test. This will be a compile and link. The script looks at the exit status. If the status shows an error, then that's good. It means the toolchain rejected the feature. In that case, the script writes a line in the output file results.txt with the test case name and a result type test. That is, the CTS link time test will detect the error. On the other hand, if the exit status is normal, then the use of the restricted feature was not detected, and the output of the script will indicate inspect. So after the script is run, you have a text file that indicates which requirements are enforced by the CTS's link time tests and which ones require source code inspection. You'll then need to enter this information in the TCATS worksheet. The U who runs the test can be the toolchain provider, the UoC supplier, or the verification authority agent. Here's another workflow, this time for what happens during an official CTS run. If you're the UoC supplier, then you follow the instructions in the toolchain support package and you've installed the relevant stub libraries. These will be the Ada Gold Standard library and the compiler-specific runtime. The CTS takes the UoC object code and tries to link it against these libraries. It's also doing some other checking, for example, related to the data model, but that's not relevant here. The CTS outputs its results in the verification report. If the report indicates success, well, that's nice, but your work isn't done. You need to show that the verification authority the inspection evidence for the requirements that are not enforced by the CTS link. You'll need evidence for each row in the spreadsheet where the verification method is marked as inspect. Actually, you're still not quite done. Don't forget, you need to show that there's no source code calls on functions from the compiler-specific runtime. Again, you'll need some inspection evidence. Finally, in some situations, a conformant UoC might get a link time failure. For example, if the UoC contains both Ada and C code, and the C code invokes functions that are permitted in the C Gold Standard library but not present in the Ada libraries, then the link will fail. The UoC supplier would need to explain why any such link errors are excusable. Okay, to sum up, first I want to emphasize that the approach described here is evolutionary rather than revolutionary. It's basically the same as for C and C++ with the CTS using link time tests against stub runtime libraries. And as with the other languages, there's no need for the software supplier to expose the source code. The main difference for Ada is that the compiler-specific library is more extensive, and the CTS needs to account for the installation of the relevant compiler-specific runtime. But both C and C++ will also need to deal with inspection evidence for some of the requirements. The work we've done on Ada has brought some lessons learned that could be adapted to the other languages. One is the TCATS concept. It'd be useful to have analogous tests for C and C++. Also, the other languages will need inspection rules for guaranteeing the absence of source code calls on functions from the compiler-specific runtime. So where are we? The approach described here and in the TIM paper is documented in FACE ticket 1070. This ticket has been approved and serves as an approved correction to the CTS. So if you have a non-OSS UoC that needs to be verified for FACE conformance, there's a process in place that can handle it. In terms of follow-up, the most immediate priority is to get a simple process for verifying conformance for mixed language UoCs, in particular for Ada and C. Almost any large Ada application will also include some C code, and it's clumsy to perform the conformance verifications sequentially. Further downstream, it would be nice to automate the job of filling out the verification matrix, verification method column in the TCATS spreadsheet. Instead of, or in addition to outputting the results.txt file, the TCATS script should enter the information directly into the spreadsheet. And finally, it would be nice to get Ada support integrated directly into the CTS. For example, running the TCATS as part of the CTS would remove some redundancy and make it easier for all the stakeholders, the toolchain vendor, the UoC supplier, and the verification authority. Okay, I would like to acknowledge some assistance from various folks. First, my colleagues at Adacore, Dana, Michael, and Dudry, who are instrumental in helping to prepare and also test the approach that we've come up with. Also, under the auspices of the OSS, we've had meetings every 2 weeks to again formulate and review this approach. So again, thanks to Robert Daniels from Vanderbilt, Patrick Kike from Green Hills, and Joel Sherrill from OAR. I'd also like to put out a special thank you to the late Chris Edwards. Back a number of years ago, when we were first coming up with the ideas for how to do ADA-phase conformance, I mentioned the problem with having the compiler-specific runtime and have that installed as part of the CTS. And I said, look, I mean, there's really no other way to do it than to have these compiler-specific, these vendor-specific runtimes installed. And Chris's first comment was, well, okay, well, how do we know that this compiler-specific runtime actually supports what's required and prohibits what's prohibited? And I mean, that was the insight. That was basically the inspiration behind the TCATs. So again, thanks to the late Chris Edwards. Okay, I think I stayed on schedule. That's always one of the criteria for these presentations. If there's any questions, I'll be happy to attempt to field them.